The data arrived on a clear night in 1968. At Kitt Peak Observatory in the mountains of southern Arizona, astronomer Vera Rubin alternated between eating ice cream cones and developing photographic plates in the darkroom. The desert heat rose from below, shimmering up from the Sonoran landscape even as night fell. But inside the observatory dome, temperatures were controlled, steady. Her colleague, Kent Ford, operated their revolutionary image tube spectrograph, capturing light from the Andromeda Galaxy that had traveled across 2.5 million light-years of space to reach their telescope. They were measuring something simple, or so it seemed: how fast stars orbit around the galactic center. This was fundamental astronomy, the kind of observation that had been done for decades in our own solar system. Measure the position of an object, measure it again later, calculate the velocity. The technique was straightforward, but the implications of what they would find were anything but simple. By the end of that first night, after 4 ice cream cones and hours of careful work, Rubin recalled later, they were puzzled by what they saw. The rotation curve wasn't behaving as expected. It wasn't falling off the way it should. Stars at the edge of the galaxy were moving just as fast as stars near the center, maintaining velocities of around 250 kilometers per second, even at distances where the visible light of the galaxy faded to almost nothing. According to everything they knew about gravity and orbital mechanics, this shouldn't be possible. Those outer stars should have been moving slowly, lazily, held by the weak gravitational tug of the distant galactic core. Instead, they were racing around at impossible speeds. By all rights, the galaxies should have been flying apart, their outer regions flung into intergalactic space like water droplets from a spinning wheel. What Vera Rubin discovered that night would transform our understanding of the universe. She had found evidence for something invisible, something that doesn't emit light or absorb it, something that exerts gravitational force but reveals itself in no other way, something that makes up most of the matter in the cosmos. Vera Florence Cooper was born in Philadelphia in 1928 to immigrant parents who encouraged her curiosity about the night sky. As a young girl, she built a cardboard telescope with her father's help and watched stars wheel across the darkness outside her window, tracking their motions on homemade star charts. That fascination never left her. By the time she was 10, she knew she wanted to be an astronomer. It was an unusual ambition for a girl in the 1,930 but her parents supported her dream. Her father, an electrical engineer, helped her construct increasingly sophisticated observing equipment. Her mother drove her to meetings of amateur astronomers. She earned her bachelor's degree in astronomy from Vassar College in 1948, graduating as the only astronomy major in her class. The isolation didn't deter her. If anything, it prepared her for what was to come. When she applied to Princeton for graduate school, she received a curt response. Princeton does not accept women in the astronomy program. That policy wouldn't change until 1975. Nearly 3 decades later, the rejection stung. But Rubin had learned early that closed doors were simply obstacles to be circumvented. Undaunted, Rubin went to Cornell, where she studied under physicists Philip Morrison, Richard Feynman, and Hans Bethe, titans of 20th century physics. For her master's thesis, she investigated large-scale motions of galaxies, discovering what would later be called the supergalactic plane, a flattened distribution of galaxy clusters that defines the equator of our home supercluster. It was groundbreaking work, suggesting that the universe had structure on scales far larger than anyone had imagined. When she presented her findings at the American Astronomical Society meeting in 1950, the response was hostile. One colleague later described her work as sloppy. Another suggested she must have made an error in her calculations. The skepticism was tinged with something else, something unspoken. A young woman, barely out of her undergraduate education, was proposing to overturn established ideas about the universe. The astronomical community wasn't ready to listen, but she persisted. She always persisted. She went on to earn her PhD from Georgetown University in 1954, studying under George Gamow, the physicist who would later be recognized for his work on Big Bang cosmology. Her doctoral thesis examined the rotation of galaxies and large-scale streaming motions in the universe. Again, her work was ahead of its time. The patterns she identified in galactic motions wouldn't be fully understood until decades later, when cosmologists developed detailed models of large-scale structure formation. In the early 1960s, Rubin joined the Carnegie Institution of Washington's Department of Terrestrial Magnetism. The department was a unique place, focused on geophysics and planetary science, but open to broader questions about the universe. It gave researchers freedom to pursue unconventional ideas. For Rubin, after years of teaching and juggling family responsibilities, she and her husband Bob had 4 children, all of whom would eventually become scientists. Time and resources to conduct her own observations, rather than relying on other people's data. There, she met Kent Ford, a staff astronomer who had developed something remarkable: an image tube spectrograph. The device was a revolution in astronomical instrumentation. Traditional spectroscopy required long photographic exposures, sometimes many hours, to gather enough light from distant galaxies. Ford's instrument used an electronic image intensifier, a technology borrowed from military night vision equipment, to amplify faint light signals by a factor of about 10,000. This device could measure the velocities of stars with unprecedented precision by analyzing the wavelengths of light they emitted, and it could do so in a fraction of the time required by conventional methods. Where traditional photographic plates might require hours of exposure, Ford's spectrograph could do the same work in minutes. Rubin immediately recognized its potential for studying how galaxies rotate. The image tube spectrograph could capture the spectra of individual regions within a galaxy, measuring how fast different parts were moving. By positioning the spectrograph's slit along the major axis of a galaxy and capturing the Doppler shifts of emission lines from ionized hydrogen gas, astronomers could map out a galaxy's rotation curve with precision. This was exactly the tool needed to answer fundamental questions about galactic dynamics. The principle was straightforward, rooted in physics that Isaac Newton had worked out 3 centuries earlier. Just as planets in our solar system orbit the sun, stars orbit the centers of their galaxies. The relationship between orbital velocity and distance from the center of mass follows from the law of universal gravitation. In the solar system, this relationship is clear and unambiguous. Mercury, the innermost planet, circles the sun at a blistering 47 kilometers per second, completing an orbit every 88 Earth days. Earth, farther out, moves at a more sedate 30 kilometers per second, taking 365 days to complete its circuit. Neptune, in the cold outer reaches of the solar system, crawls along at just 5 kilometers per second, requiring 165 Earth years to orbit once around the Sunday. This relationship, described by Kepler's third law and explained by Newton's law of gravitation, follows a simple mathematical pattern. The orbital velocity decreases with the square root of the distance from the central mass. Double the distance, and the velocity drops by a factor of 1.4. Move 10 times farther out, and the velocity becomes roughly 1/3 of what it was. This is because the gravitational force weakens with distance. The farther you are from the center of mass, the weaker the gravitational pull, and the slower you need to move to maintain a stable orbit. Rubin and Ford expected to see the same pattern in galaxies. Most of a galaxy's visible mass appears concentrated in its bright central bulge, where billions of stars crowd together. Stars far from the center, in the sparse outer regions of the galactic disk, should be moving slowly, held by the weak gravitational pull of that distant core. If you plotted velocity against distance, you should see a curve that rises near the center, peaks somewhere in the middle regions, where you're measuring the combined effect of the central bulge and the disk, and then falls off gradually at larger radii. That falling portion of the curve, the Keplerian decline, was what theory predicted, but that's not what they found. Not even close. At Kitt Peak and later at Lowell Observatory, Rubin and Ford systematically observed spiral galaxy after spiral galaxy. They placed their spectrograph slit along the major axis of each galaxy and measured the Doppler shifts of hydrogen emission regions. Stars moving toward Earth showed their light shifted slightly toward the blue end of the spectrum. Stars moving away showed a shift toward red. From these shifts, they could calculate precise velocities. Night after night, the pattern repeated. The rotation curves were flat. Stars at the outer edges of galaxies were moving at 200 or 250 kilometers per second, the same speeds as stars much closer to the galactic center. This was wrong. Profoundly wrong. If the visible stars represented most of the galaxy's mass, those outer stars should have been moving at perhaps 50 or 100 kilometers per second, slow enough that their velocity curves would show a clear downward slope. Instead, the curves stayed level, flat as a Kansas horizon. The galaxies were rotating like solid disks, not like collections of stars held together by their mutual gravity. Rubin and Ford expanded their survey. They observed 60 spiral galaxies, then more. The flat rotation curves appeared again and again. There were no exceptions. In 1978, they published their systematic findings in a series of papers in the Astrophysical Journal. The titles were carefully worded, scientific, precise. Either Newton's laws of motion and gravity were fundamentally wrong, or galaxies contained enormous amounts of invisible matter. If you wanted to keep Newton's laws, you had to accept that galaxies are embedded in vast halos of something that doesn't shine, something that exerts gravitational force but emits no light, something dark. Rubin herself was cautious in her conclusions. She didn't immediately leap to the term dark matter. She let the data speak. But gradually, as other teams confirmed her results through independent methods, including radio observations of hydrogen gas and X-ray studies of galaxy clusters, a picture emerged. Galaxies are not what they appear to be. What we see, the glowing stars and nebulae captured by telescopes, represents only a small fraction of what's actually there. Rubin's calculations showed that galaxies must contain at least 5 to 10 times more mass than can be accounted for by visible matter. By the early 1980 seconds, dark matter had moved from speculation to a central pillar of astrophysics. The evidence was overwhelming. The flat rotation curves, the measured velocities of galaxies within clusters, the gravitational lensing observations that would come later, all pointed to the same conclusion. Most of the matter in the universe is invisible. At least 85% of the matter in the cosmos doesn't emit, absorb, or reflect light. It reveals itself only through gravity, through its influence on things we can see. It is, by definition, dark. The missing mass problem, as it came to be known, wasn't actually new. In 1933, 40 years before Rubin's systematic observations, a Swiss astronomer named Fritz Zwicky had studied the Coma cluster, a collection of more than 1,000 galaxies bound together by gravity, located 330 million light-years from Earth. Zwicky measured the velocities of individual galaxies within the cluster, using the Doppler effect. What he found puzzled him. The galaxies were moving too fast. When you observe a gravitationally bound system, whether it's the solar system or a galaxy cluster, you can estimate the total mass by measuring how fast things are moving. The faster objects move, the more mass is required to hold them in orbit. Otherwise, they would escape into space. Zwicky calculated that the galaxies in the Coma cluster were moving so fast that the cluster should have dispersed long ago, unless there was additional mass, invisible mass, holding it together. He estimated that the cluster must contain at least 400 times more mass than could be accounted for by the visible galaxies alone. He called this unseen material Dunkel materia, dark matter. But Zwicky's proposal was too radical, too outrageous for his colleagues to accept. The idea that the universe was dominated by invisible matter seemed like science fiction. For nearly 4 decades, his work was largely ignored or dismissed. It took Rubin's meticulous, systematic observations, her flat rotation curves repeated across dozens of galaxies, to force the astronomical community to confront the reality. The dark matter hypothesis could no longer be avoided. Once astronomers accepted that dark matter existed, they had to figure out what it might be. The first thought was that perhaps the missing mass consisted of ordinary matter that simply wasn't glowing. Cold hydrogen gas floating between galaxies. Failed stars called brown dwarfs, too small to ignite nuclear fusion. White dwarfs, the cooling remnants of dead stars. Neutron stars, or black holes. Collectively, these objects were called MACOs, an acronym for Massive Compact Halo Objects. Throughout the 1,990 seconds, astronomers searched for MACOs by looking for gravitational microlensing events, brief brightenings of distant stars caused by an invisible object passing between the star and Earth. They found some evidence for MACOs, but nowhere near enough to account for the missing mass. The MACO and EROS experiments eventually showed that objects less massive than 1/10 of a solar mass make an insignificant contribution to galactic dark matter. MACOs couldn't solve the problem. Moreover, evidence from other areas of cosmology pointed away from ordinary matter. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, allowed physicists to calculate how much ordinary matter, baryonic matter made of protons and neutrons, exists in the universe. The answer was clear. Ordinary matter accounts for only about 5% of the universe's total mass energy content. Dark energy, the mysterious force accelerating cosmic expansion, makes up about 68%. Dark matter accounts for the remaining 27%. Whatever dark matter is, it's not made of atoms. It's not baryonic. It's something fundamentally different. This realization opened a new chapter in physics. Dark matter became a problem not just for astronomers, but for particle physicists. If dark matter isn't made of ordinary atoms, then it must consist of exotic particles that don't interact with light. Particles that have mass, that exert gravitational force, but that pass through ordinary matter like ghosts. Particles that were produced in vast quantities in the early universe, and that still surround us, streaming through the Earth, through our bodies, undetected and undetectable except through their gravitational effects. The search for these particles would drive decades of experimental work, construction of elaborate detectors deep underground, far from cosmic rays and background radiation. But before we explore that search, we need to look at some of the strangest objects dark matter has created. Galaxies that are almost entirely invisible. Ghost galaxies. In 2015, astronomers using the Dragonfly telephoto array announced a discovery that seemed almost impossible. The Dragonfly array, built by astronomers Peter van Dokkum of Yale University and Roberto Abraham of the University of Toronto, consists of multiple telephoto camera lenses working together to detect extremely faint, low surface brightness objects in the sky. The array was specifically designed to find things that conventional telescopes miss, objects so dim and diffuse that they blend into the background glow of the night sky. What they found in the Coma cluster were galaxies unlike any seen before. These galaxies were enormous, comparable in size to the Milky Way, with diameters of 60,000 light-years or more, but they emitted only a tiny fraction of the light. Where the Milky Way contains 200 to 400 billion stars, these ghostly galaxies seem to contain only a few billion stars, scattered so sparsely that the galaxies appeared as faint smudges on photographic plates. They were called ultra-diffuse galaxies. or UDGs. Ultra-diffuse galaxies are not small. They are not dwarf galaxies. They have the physical dimensions of large spiral galaxies like our own. But their luminosity, their brightness, is comparable to that of dwarf galaxies. It's as if someone took a normal galaxy and spread its stars out across a much larger volume, diluting the light. The resulting object has such low surface brightness that it's nearly invisible. In surveys of the night sky, these galaxies are easy to miss entirely. The challenge is to filter out background noise without accidentally filtering out the galaxies themselves. Once astronomers knew what to look for, they found UDGs everywhere. More than 1,000 ultra-diffuse galaxies have now been cataloged, most of them in galaxy clusters like Coma, Virgo, and Fornax. They appear to be abundant, perhaps representing a significant population of galaxies that had been hiding in plain sight all along. Their distribution within clusters mirrors that of brighter galaxies, suggesting they formed through similar processes and are genuine members of their host clusters. But what makes UDGs so diffuse? Why are they so large yet so faint? And more critically for our story, what are they made of? These questions led astronomers to one of the most peculiar objects ever discovered, a galaxy that might be made almost entirely of dark matter. Dragonfly 44. The galaxy was discovered during the Dragonfly Array survey of the Coma cluster. It appeared as an extremely faint spheroidal smudge, peppered with compact sources that turned out to be globular clusters, ancient spherical collections of stars that orbit the galaxy. At first glance, Dragonfly 44 didn't seem particularly special. It was one of many UDGs, but when Van Dokkum and his colleagues looked closer, they realized something extraordinary. The galaxy was massive, very massive. Despite emitting only 1% of the light of the Milky Way, Dragonfly 44 appeared to contain roughly the same total mass as our galaxy. This estimate came from measuring how fast stars move within the galaxy, a technique called velocity dispersion. When you measure the spread of velocities among a galaxy's stars, you can infer the total gravitational mass holding them together. The more massive the galaxy, the faster its stars move. To get precise measurements, Van Dokkum's team used the Deep Imaging Multi-Object Spectrograph, called DEMOS, on the Keck 2 telescope in Hawaii. Over 6 nights, they collected 33.5 hours of spectroscopic data, measuring the velocities of stars in Dragonfly 44. The luminosity-weighted velocity dispersion they measured was 33 kilometers per second, with a margin of error of plus or minus 3 kilometers per second. This might not sound fast, but for a galaxy emitting so little light, it was shockingly high. Using these velocity measurements, the team calculated that Dragonfly 44 must have a mass of approximately 1 trillion solar masses. That's comparable to the Milky Way. Yet the galaxy emits only 1% of our galaxy's light. If you divide mass by luminosity, you get a mass-to-light ratio that is extraordinarily high. Most of the galaxy's mass is not in stars. Most of the galaxy's mass is dark. The team also counted the globular clusters orbiting Dragonfly 44. Globular clusters are useful because their number typically correlates with the total mass of a galaxy. Massive galaxies have many globular clusters. Dwarf galaxies have few. Van Dokkum's initial count suggested Dragonfly 44 hosted about 90 globular clusters, which would be consistent with a Milky Way mass galaxy. Everything pointed to the same conclusion. A galaxy that somehow failed to form stars efficiently, leaving behind a dark matter halo populated by a skeleton of ancient stars and globular clusters. If the initial estimates were correct, Dragonfly 44 would be nearly 100% dark matter. Some early calculations suggested it might be 99.99% dark matter, almost entirely invisible, a ghost. The announcement in 2016 made headlines. Here was direct evidence for a galaxy dominated by dark matter, a laboratory for studying dark matter's properties in an environment where ordinary matter played almost no role. The implications were profound. If galaxies like Dragonfly 44 existed, it meant dark matter halos could form and persist even in the absence of significant star formation. It meant the relationship between dark matter and visible matter was more complex than anyone had imagined. But science progresses through skepticism and further observation. Not everyone was convinced by the initial findings. The measurements were extraordinarily difficult. The galaxy was extremely faint, a ghostly smudge on photographic plates. The velocity dispersion measurements depended on capturing light from a handful of stars or globular clusters scattered across the galaxy. Each observation required hours of telescope time to gather sufficient photons. Some astronomers questioned whether the mass estimate was too high. Could the globular cluster count be wrong? These were legitimate scientific questions, the kind that drive astronomy forward. In 2019, a team led by Taimour Saifulahi published new observations of Dragonfly 44 using the Keck Cosmic Web Imager, a state-of-the-art spectrograph capable of spatially resolved spectroscopy. They gathered 25.3 hours of observing time, an enormous investment of telescope resources, to map the velocity field across the galaxy with unprecedented detail. Their analysis painted a different picture. The velocity dispersion was indeed around 33 kilometers per second, within the half-light radius, confirming the earlier measurements on that point. But when they carefully modeled the galaxy's mass distribution and accounted for the orbital motions of stars, when they considered the possibility that the dark matter halo might have a core rather than a cusp, when they factored in all the complexities of gravitational dynamics, they calculated a total mass of about 160 billion solar masses, not 1 trillion, 6 times less than the original estimate. Still massive by the standards of ultra-diffuse galaxies, still requiring a substantial dark matter component to explain, but an order of magnitude less than the Milky Way. Moreover, additional studies found that Dragonfly 44 hosts only about 20 globular clusters, not the 90 initially reported. The discrepancy arose from the difficulty of identifying globular clusters in such a diffuse, faint galaxy. Some of the objects initially counted as globular clusters turned out to be background galaxies or foreground stars. When only the confirmed globular clusters were counted, the number dropped dramatically. And a smaller globular cluster count is consistent with a lower total mass. The two independent measurements now agreed. X-ray observations with the Chandra and XMM Newton space telescopes failed to detect any hot gas around the galaxy. This was significant. If Dragonfly 44 resided in a massive dark matter halo, comparable to the Milky Way's, that halo would create a deep gravitational potential well. Gas falling into such a potential well would be shock-heated to tens of millions of degrees Kelvin and would emit X-rays. The absence of X-ray emission placed strong upper limits on the mass of the dark matter halo. Those limits were incompatible with the original trillion solar mass estimate. The dark matter halo is there, certainly, but it's not as massive as initially thought. So what is Dragonfly 44? The debate continues. Some astronomers still argue it's a failed Milky Way, a galaxy that formed in a massive dark matter halo but somehow failed to convert gas into stars. Perhaps strong winds or radiation from nearby galaxies stripped away the star-forming gas early in the galaxy's history, leaving behind a dark matter halo with only a few stars. This scenario is called the high-spin hypothesis. Two smaller galaxies, rotating in the same direction, merged to form Dragonfly 44. The merger gave the galaxy high angular momentum, puffing it out and blowing away gas before stars could form. Others argue that Dragonfly 44 is not a failed large galaxy but rather a successful large dwarf galaxy. a galaxy that formed in a relatively low-mass dark matter halo and grew to its current size through gradual accretion and mergers. In this view, Dragonfly 44 resembles other dwarf spheroidal galaxies, just larger and more diffuse than usual. The dark matter content is significant but not extraordinary. The truth is, we don't yet know for certain. What we do know is that Dragonfly 44 and ultra-diffuse galaxies like it have opened a new window into how galaxies form and evolve. These objects force us to confront the diversity of galaxies in the universe. Not all galaxies follow the same path. Some are bright and full of stars, some are dim and diffuse, some appear to be dominated by dark matter, and strangely, some ultra-diffuse galaxies seem to contain almost no dark matter at all. A galaxy called NGC 1052DF2, discovered in 2018, appears to have a mass-to-light ratio consistent with its visible stars alone. If confirmed, it would mean galaxies can form without dark matter, which would be equally mysterious. The universe, it seems, produces ghost galaxies in many forms. Some are ghosts because they are mostly dark matter. Some are ghosts because they are mostly ordinary matter, but too diffuse to see easily. Each one is a puzzle, a clue in the larger mystery of what dark matter is and how it shapes the cosmos. If dark matter is real, if it truly makes up 85% of the matter in the universe, then what is it made of? What particles could have the right properties, could interact weakly enough with ordinary matter to remain invisible, yet still exert gravitational force? Particle physicists have proposed many candidates over the decades, but two have emerged as the most compelling. Let's start with WIMPs. The acronym stands for Weakly Interacting Massive Particles. The name is descriptive. These would be particles with significant mass, perhaps 100 times heavier than a proton, that interact with ordinary matter primarily through the weak nuclear force and gravity. The weak force is one of the four fundamental forces of nature. It's responsible for radioactive decay and certain types of particle interactions. It's much weaker than the electromagnetic force, but stronger than gravity. WIMPs became the leading dark matter candidate in the 1980 seconds because they fit beautifully with a broader theory in particle physics called supersymmetry. Supersymmetry, or SUSY for short, proposes that every known particle in the Standard Model has a heavier partner particle with different quantum properties. The electron has a partner called the selectron. The quark has a partner called the squark. The photon has a partner called the photino. The neutrino has a partner called the neutralino. These partner particles have never been observed, but if supersymmetry is correct, if nature truly exhibits this fundamental symmetry between fermions and bosons, the theory is elegant, solving several problems in particle physics beyond just dark matter. It helps explain why the Higgs boson has the mass it does, preventing certain quantum corrections from driving the Higgs mass to absurdly high values. It provides a pathway toward unifying the fundamental forces of nature. And most importantly for dark matter, it naturally predicts particles with exactly the right properties. The lightest supersymmetric particle, whatever it turns out to be, most likely some combination of photinos, xenos, and Higgsinos called the neutralino, would be stable. It couldn't decay into anything lighter because there would be nothing lighter for it to decay into. And if this lightest particle is stable and has the right mass, it would have been produced in enormous quantities in the early universe. As the universe cooled after the Big Bang, these particles would have frozen out of thermal equilibrium at a specific temperature, leaving behind a relic density that happens to match the observed dark matter density today with remarkable precision. This coincidence, the fact that the predicted relic abundance matches observations so well, is sometimes called the WIMP miracle. Consider what it means. A particle with weak force interaction strength, with a mass somewhere in the range of 100 to 1000 giga-electron volts, naturally produces the right amount of dark matter when you run the calculations forward from the Big Bang. The numbers just work out. No fine-tuning required. No additional assumptions needed. The weak force, with its characteristic interaction strength, produces dark matter at precisely the density we observe. It seemed too perfect to be accidental. Many physicists believed WIMPs had to exist. Nature wouldn't have arranged things so neatly by chance. The search for WIMPs began in earnest in the 1990 seconds. The basic idea is straightforward. If WIMPs exist, they should be streaming through the solar system right now, part of the dark matter halo surrounding the Milky Way. Occasionally, very rarely, a WIMP might collide with an atomic nucleus in ordinary matter. When it does, it would transfer a tiny amount of energy, causing the nucleus to recoil. If you could build a detector sensitive enough to measure these nuclear recoils, you could detect dark matter directly. The challenge is that the expected interaction rate is extraordinarily low. A WIMP might pass through a ton of ordinary matter and interact only once per year, or once per decade, or perhaps never. The interaction cross-section, the measure of how likely a WIMP is to scatter off a nucleus, could be as small as 10 to the power of negative 46 square centimeters. That's a billionth of a billionth of a billionth of a billionth of a square centimeter. To have any hope of detection, you need a large detector mass to maximize the number of potential target nuclei. And you need to eliminate all sources of background noise that could mimic a WIMP signal. Every source of radiation becomes a problem. Cosmic rays from space, natural radioactivity in the surrounding rock, radioactive isotopes in the detector materials themselves, radon gas seeping up from the ground. Even the concrete used to build the laboratory can contain trace amounts of radioactive elements that will swamp any potential WIMP signal. When a cosmic ray muon passes through your detector, it can create nuclear recoils that look exactly like what a WIMP would produce. When uranium or thorium in the rock decays, it emits gamma rays and neutrons that can scatter off nuclei. These are all backgrounds, noise that obscures the signal you're trying to find. That's why dark matter detectors are built deep underground. The Lux Zeppelin experiment, called LZ, operates 4,850 feet below the surface at the Sanford Underground Research Facility in South Dakota, in a former gold mine. The rock above provides shielding from cosmic rays. A cosmic ray muon that would easily penetrate a few meters of concrete must now traverse nearly a mile of rock. Most don't make it through. The cosmic ray flux is reduced by a factor of about 100,000 compared to the surface. But even deep underground, you're not completely shielded. Some cosmic ray muons still get through. Radioactivity is still present. The detector must be exquisitely sensitive while also being exquisitely discriminating. The LZ detector itself consists of 7 tons of ultra-pure liquid xenon cooled to minus 100 degrees Celsius. Xenon is chosen because it's a heavy element with a large nucleus, making it a good target for WIMP collisions, and because liquid xenon can serve as both the target material and the detection medium. When a particle interacts with a xenon nucleus, the recoil produces 2 signals: a prompt flash of scintillation light as electrons in the xenon atoms are excited and then relax, and a delayed pulse of electrons that are drifted by an electric field to collection electrodes at the top of the detector. By measuring both the light signal and the charge signal, and by examining the ratio between them and the spatial distribution of the interaction, experimenters can distinguish nuclear recoils, which could be caused by WIMPs, from electronic recoils, which are typically caused by gamma rays and other background radiation. Every component of the detector was carefully screened for radioactivity. Every nut and bolt, every wire and seal, every O-ring and gasket. The screening process took 5 years. materials were tested in ultra-sensitive germanium detectors to measure their radioactive contamination. Only the cleanest materials, those with radioactivity levels below a few parts per trillion, were allowed into the detector. Even trace amounts of radioactive contaminants could overwhelm the signal. The goal is to create the quietest possible environment, a place where the whisper of a WIMP interaction might be heard above the background noise. LZ began operations in late 2021. Similar experiments, XENONT in Italy and Panda X4 tons in China, also use multi-ton liquid xenon detectors. Other experiments use different target materials. The Super CDMS Snow Lab experiment uses silicon and germanium crystals cooled to near absolute zero. The Deep 3600 experiment uses liquid argon. Each detector has different sensitivities to different WIMP masses. Together, they cover a wide range of possibilities. So far, none of these experiments has detected a WIMP. The lack of detection has pushed the sensitivity limits further and further. If WIMPs exist and have interaction cross-sections in the range originally predicted by supersymmetry, they should have been detected by now. The experiments are sensitive enough. The fact that nothing has been found is beginning to worry physicists. It doesn't mean WIMPs don't exist. They could interact even more weakly than expected, but it does mean the simplest WIMP models are in trouble. Adding to the concern, the Large Hadron Collider at CERN, which was expected to produce supersymmetric particles in proton-proton collisions, has found no evidence for supersymmetry. The Higgs boson was discovered in 2012, a triumph for the Standard Model, but none of the super-partner particles have appeared. The mass range, where they were expected to show up, has been largely ruled out. Does this mean WIMPs are ruled out? No, but it means we need to think more broadly. The search continues, with experiments becoming more sensitive each year. Eventually, if WIMPs exist in the mass and interaction range still allowed by observations, they will be found. Or the experiments will rule them out entirely, forcing physicists to look elsewhere. Which brings us to the other leading candidate. The particle that has been gaining favor as WIMPs remain elusive. The axion. Axions are not a new idea. They were first proposed in 1977 by physicists Roberto Peccei and Helen Quinn as a solution to a completely different problem in particle physics called the strong CP problem. The details are technical, but the essence is this: the theory of quantum chromodynamics, which describes how quarks and gluons interact via the strong nuclear force, allows for certain symmetry-violating effects that should cause measurable CP violation, a difference between matter and antimatter. But experimentally, no such violation is observed. The theory predicts something that doesn't happen. Why? Peccei and Quinn proposed a new symmetry that would naturally explain the absence of strong CP violation. But when you introduce a new symmetry into a theory, you often introduce a new particle. The particle associated with the Peccei-Quinn symmetry was named the axion after a brand of laundry detergent because it cleaned up the strong CP problem. Axions, if they exist, would be extraordinarily light, perhaps a millionth of an electron volt, or even lighter. For comparison, an electron has a mass of about 511,000 electron volts. An axion would be 1 trillion times lighter. They would be so light that they behave less like particles and more like waves, similar to photons. They would interact with ordinary matter incredibly weakly, primarily through their coupling to electromagnetic fields. They would barely interact at all, hence the nickname invisible axions. For years, axions were considered an interesting theoretical curiosity, but not a serious dark matter candidate. They were too light, too weakly interacting. If axions were produced in the early universe through a mechanism called the misalignment mechanism, they could be produced in enormous, quantities, not through thermal production, like WIMPs, but through a quantum field process that would flood the universe with axions. These axions would be moving slowly, cold, clumping together under gravity just like dark matter should. And because each individual axion is so light, you would need an enormous number of them to account for the observed dark matter density. The numbers worked out. Axions could be dark matter. The challenge is detecting them. Axions are so weakly interacting that they pass through ordinary matter even more easily than WIMPs. But axions have a special property. In the presence of a strong magnetic field, an axion can convert into a photon, a particle of light. The conversion probability is tiny, but it's not zero. If you put a strong magnet inside a microwave cavity and tune the cavity to resonate at the right frequency, axions passing through the cavity could convert into photons. Those photons would add energy to the cavity, producing a faint signal that could, in principle, be detected. This is the principle behind the Axion Dark Matter Experiment, ADMX, at the University of Washington. The experiment uses a large superconducting magnet to create a magnetic field of several Tesla, similar in strength to an MRI machine. Inside the magnet is a cylindrical cavity cooled to a fraction of a degree above absolute zero. The cavity can be tuned to different resonant frequencies, scanning across the possible mass range for axions. If axions exist and have a mass corresponding to the cavity's resonant frequency, they will convert into microwave photons. The signal would be exceptionally weak, on the order of 10 to the power of -23 watts, less than a trillionth of a watt. But with quantum-limited amplifiers and careful signal processing, it should be detectable. ADMX began operations in the 1,990 seconds, but only recently achieved the sensitivity required to detect the most theoretically favored axions. In April 2018, the experiment reached the sensitivity needed to detect axions produced by the misalignment mechanism. If they're there, ADMX could find them. The experiment scans slowly through frequency space, spending weeks or months at each frequency to gather enough data. So far, no axion signal has been detected, but the search has only covered a fraction of the possible mass range. The search continues. Other experiments are exploring different approaches. The Abracadabra experiment at MIT uses a toroidal magnet, shaped like a donut. The magnetic field circulates around the torus. An axion interacting with this field would create a small magnetic flux through the hole in the center of the donut, the place where the munchkin would be if the torus were an actual pastry. This flux could be detected with sensitive magnetometers. The CERN Axion Solar Telescope, CAST, took a different approach. Instead of searching for dark matter axions from the galactic halo, CAST looked for axions produced in the sundae. The sun's core is hot and dense, and theoretical models predict that axions could be produced there through interactions with photons and electrons. These solar axions would stream out from the sun and could be detected on Earth if they convert back into X-ray photons in a magnetic field. CAST operated for many years, pointing at the sun and searching for excess X-rays. No axions were detected, but the experiment set important limits on axion properties. A new experiment, the International Axion Observatory, IAXO, is under development and will be 100 times more sensitive than CAST. If solar axions exist in the theoretically predicted range, IAXO should find them. Why has interest in axions grown while enthusiasm for WIMPs has waned? Partly because WIMPs should have been easier to find. If they exist with the properties originally predicted, multiple experiments should have detected them by now. The fact that they haven't suggests either they don't exist or they're much harder to detect than expected. The experiments are just now reaching the required sensitivity. Moreover, axions solve two problems at once. They address the strong CP problem in quantum chromodynamics, and they could be dark matter. That theoretical elegance is appealing. Nature might prefer solutions that kill two birds with one stone, but we should be cautious. Neither WIMPs nor Axions have been detected. Both remain hypothetical. Dark matter could be something else entirely: sterile neutrinos, primordial black holes, self-interacting dark matter particles, or perhaps something we haven't even imagined yet. The universe has surprised us before. If dark matter is invisible, how do we know where it is? How can we map something that doesn't emit light? The answer comes from one of Einstein's most profound insights: mass bends space. In 1915, Albert Einstein published his general theory of relativity, which describes gravity not as a force, but as a curvature of space-time. Massive objects like stars and galaxies create indentations in the fabric of space-time, and other objects move along the curved paths created by those indentations. One of the predictions of general relativity is that light, despite having no mass, should follow these curves. This prediction was spectacularly confirmed during a solar eclipse in 1919, when astronomers observed that stars near the sun appeared shifted from their usual positions. The sun's gravity had bent the starlight. Einstein became world famous overnight. But the implications of gravitational lensing, as this phenomenon is called, would take decades to fully explore. If a very massive object, like a galaxy cluster, lies between us and a more distant galaxy, the light from that distant galaxy is bent as it passes through the cluster's gravitational field. From our perspective on Earth, the distant galaxy appears distorted, stretched, sometimes forming arcs or multiple images. This is called strong gravitational lensing, and it creates some of the most beautiful images in astronomy: rings and arcs of light wrapped around massive clusters. Even when the lensing effect is too weak to create obvious distortions, it still subtly stretches and shears the images of background galaxies. By measuring the shapes of many background galaxies statistically, astronomers can reconstruct the distribution of mass in the foreground cluster. This technique, called weak gravitational lensing, is one of the most powerful tools we have for mapping dark matter. Here's why it's so important. Gravitational lensing doesn't care what kind of mass is doing the lensing. It responds to all mass equally, treating dark matter and ordinary matter with perfect impartiality. Light bends in response to the total gravitational field, the cumulative effect of everything that has mass. By measuring the lensing signal produced by a galaxy cluster, by carefully analyzing how the images of thousands of background galaxies are distorted, we can reconstruct the distribution of mass in the foreground cluster. We can create a map showing where the matter is, regardless of whether that matter emits light. The technique works like this. Background galaxies, billions of light years behind the cluster, emit light that travels through the universe toward us. When that light passes through the gravitational field of the cluster, it's deflected. Each individual photon follows a curved path through space-time. From our perspective on Earth, the background galaxy appears shifted from its true position. If the lensing is strong enough, a single galaxy might appear multiple times, its light taking different paths around the cluster and arriving at Earth from different apparent directions. Or the galaxy might be stretched into an arc, its circular shape transformed into a crescent by the differential deflection of light passing through different parts of the cluster's gravitational field. But weak lensing is subtler and, in many ways, more powerful. Even when the lensing effect is too weak to create obvious multiple images or dramatic arcs, it still subtly stretches and shears the shapes of background galaxies. A galaxy that would appear circular if viewed without lensing appears slightly elliptical. The degree of ellipticity and the orientation of the ellipse depends on the mass distribution of the foreground cluster. By measuring the shapes of many background galaxies statistically, thousands or tens of thousands of them, and by analyzing the pattern of shape distortions across the field of view, astronomers can reconstruct where the mass is and how much of it there is. This statistical approach is essential because we don't know the intrinsic shape of any individual background galaxy. Some galaxies are naturally elliptical. Some are naturally circular. Some are seen edge-on, some face-on. But if you average over thousands of galaxies, the intrinsic shapes average out to zero net alignment. Any coherent pattern of alignment, any tendency for galaxies in one region of the sky to be stretched in a particular direction, must come from gravitational lensing. The mathematics is complex, involving careful measurements of ellipticities, corrections for point spread function effects from the atmosphere and telescope optics, and sophisticated statistical analysis. But the result is a mass map, a picture of where the matter is. Nowhere is this more dramatically illustrated than in the Bullet Cluster. The Bullet Cluster, officially designated 1E06 57-56, is a pair of galaxy clusters that collided roughly 150 million years ago. The collision occurred nearly in the plane of the sky as viewed from Earth, meaning we're seeing the aftermath almost side-on. The cluster is located about 3.7 billion light-years away in the constellation Carina. When two galaxy clusters collide, different components behave differently. The galaxies themselves, being mostly empty space, pass through each other like bullets through fog. Stars within galaxies rarely collide because the distances between stars are enormous compared to their sizes. The galaxies emerge from the collision largely unscathed, gravitationally slowed, but otherwise intact. The hot gas, however, interacts strongly. Galaxy clusters contain vast amounts of gas, much more mass in gas than in stars. This gas is superheated to tens of millions of degrees Kelvin and emits X-rays. When two clusters collide, the gases interact electromagnetically. They collide, they shock, they heat up even more. The collision slows the gas dramatically. Friction strips the gas away from the galaxies. Dark matter, if the standard theory is correct, should pass through the collision like the galaxies do. Dark matter particles are collisionless. They interact only through gravity and perhaps extremely weakly through some other unknown force. During a cluster collision, dark matter halos should sail through each other, largely unaffected. This is exactly what we see in the Bullet Cluster. Observations with NASA's Chandra X-ray Observatory show two clumps of hot gas, one larger and one smaller, displaced from the centers of the galaxy clusters. The smaller clump, the bullet, has a distinctive bow-shock shape, like the shockwave in front of a supersonic jet. This gas has been stripped from its host galaxies during the collision and now lags behind. When astronomers mapped the mass distribution using gravitational lensing, they found something remarkable. The mass is not where the gas is. The mass, shown in blue in composite images, is centered on the galaxies, not on the hot gas shown in pink. The separation is clean and unambiguous. Most of the mass in the cluster is dark matter that passed through the collision along with the galaxies. The ordinary matter, the baryonic matter in the form of hot gas, lagged behind due to collisional interactions. The statistical significance of this separation is overwhelming. The probability that this offset between mass and gas occurred by chance is less than 1 in 10 to the power of 15, 1 in a quadrillion. The Bullet Cluster provides the most direct evidence we have for dark matter's existence. It's often called the smoking gun. Some skeptics had proposed that perhaps we don't need dark matter at all. Perhaps Newton's laws or Einstein's general relativity breaks down on large scales, and a modified theory of gravity could explain the observations. The Bullet Cluster deals a severe blow to modified gravity theories. In modified gravity, the gravitational field should follow the distribution of ordinary matter because there's nothing else to create it. But in the Bullet Cluster, the gravitational field, revealed by lensing, is displaced from the ordinary matter. There is mass where there is no visible matter. That mass is dark. Since the Bullet Cluster astronomers have observed other colliding clusters with similar properties. Max J25 4 to 1222, Abel 2744, the Pandora cluster. Each shows the same pattern. Gas slowed and separated. Galaxies and dark matter pass through. The evidence is consistent and compelling. In 2025, the James Webb Space Telescope observed the Bullet Cluster with unprecedented sensitivity, detecting far more distant background galaxies than any previous study. This expanded the dataset for gravitational lensing and allowed astronomers to refine the mass map even further. The revised measurements confirmed the earlier findings. Dark matter is there. It's real, and it dominates the cluster's mass. Gravitational lensing has become a standard tool for studying dark matter. Astronomers use it to map dark matter in individual galaxies, in galaxy groups, in massive clusters. They use it to study how dark matter is distributed on the largest scales, tracing the cosmic web, the filaments of dark matter that connect clusters across billions of light years. Every lensing observation strengthens the case for dark matter. We may not be able to see it directly, but we can see what it does. We can map its influence, trace its contours, measure its mass. The ghost becomes visible through the shadows it casts. Observing dark matter through its gravitational effects tells us it exists and roughly how it's distributed. But to truly understand how dark matter shapes the universe, how galaxies and clusters form, we need to simulate the process. We need to run the movie backward, starting from the early universe and watching structure grow. This is where computational cosmology comes in. Using powerful supercomputers, physicists simulate the evolution of dark matter on cosmological scales, following billions or even trillions of particles as they move under gravity. These n-body simulations have become one of the most important tools in modern cosmology. The basic idea is elegant, though the execution is extraordinarily complex. You start with a model of the early universe shortly after the Big Bang. At this time, roughly 380,000 years after the universe began, the cosmos was nearly smooth but contained tiny density fluctuations, slightly overdense and underdense regions imprinted by quantum fluctuations during the inflationary epoch in the first tiny fraction of a second after the Big Bang. These fluctuations are visible in the cosmic microwave background, the afterglow radiation from that era that still fills the universe. The CMB shows a pattern of hot and cold spots, temperature variations of only a few parts in 100,000. Those temperature variations correspond to density variations in the early universe. Slightly hotter regions were slightly underdense. Slightly cooler regions were slightly overdense. You take those density variations from the CMB observations and use them as initial conditions for your simulation. You represent the universe as a large computational volume, perhaps a cube 100 million light-years on a side, or even larger for simulations of the full observable universe. You fill this volume with millions or billions of computational particles representing dark matter. Each particle has a position, a velocity, and a mass. The particles don't represent individual dark matter particles, which would be far too numerous to simulate. Instead, each computational particle represents a large collection of real dark matter particles. Then you let gravity do its work. You evolve the system forward in time, from the early universe to the present day, a span of nearly 14 billion years. At each time step, you calculate the gravitational force each particle exerts on every other particle. This is the computational bottleneck. With a billion particles, you have a billion squared, or a quintillion, pairwise interactions to compute at each time step. Even with clever algorithms that use hierarchical tree structures or mesh-based methods to speed up the force calculations, the computational cost is enormous. Modern simulations require months of runtime on supercomputers, with thousands or tens of thousands of processor cores working in parallel. As the simulation runs, structure grows. In the early stages, the overdense regions grow denser as their enhanced gravity attracts surrounding material. Small clumps form first, tiny overdensities that collapse under their own gravity to form the first dark matter halos. These halos are small, perhaps 1,000,000 times the mass of the Sun, and they form at high redshift, when the universe was young. As time progresses, these small halos merge to form larger structures. Two halos collide, interact gravitationally, and merge into a single, more massive halo. This process continues hierarchically. Larger structures merge to form even larger ones. Small halos build up into galaxy mass halos. Galaxy mass halos merge to form group mass halos. Groups merge to form clusters. Clusters merge to form superclusters. The structure we see in the universe today, the cosmic web of filaments and voids, emerges naturally from this gravitational collapse. The simulations reproduce observed features with remarkable fidelity. The distribution of galaxy clusters, the filamentary structure connecting clusters, the vast voids where few galaxies exist, the small-scale clustering of galaxies within groups, all of it matches observations. When you compare simulation predictions with large galaxy surveys, like the Sloan Digital Sky Survey, which has mapped the positions of millions of galaxies, the agreement is striking. The simulations get the statistics right. They predict the correct abundance of halos as a function of mass, the correct clustering strength on different scales, the correct evolution of structure with cosmic time. One of the most important discoveries from these simulations is that dark matter halos have a universal density profile. No matter the mass of the halo, whether it's a dwarf galaxy or a massive cluster, the density as a function of radius follows the same functional form. This profile is called the NFW profile, named after the physicists Julio Navarro, Carlos Frank, and Simon White, who first characterized it in the 1,990 seconds. The NFW profile has a specific shape. Near the center of the halo, the density falls off as 1 over the radius. At larger radii, the density falls off as 1 over the radius cubed. There's a characteristic radius, called the scale radius, where the logarithmic slope transitions from -1 to -3. This profile is shallower than an isothermal sphere near the center and steeper at large radii. It arises naturally from the chaotic, hierarchical merging process that forms halos. Violent relaxation, the mixing and redistribution of energy during mergers, creates this specific density distribution. The simulations also predict that halos are not spherical. They are triaxial ellipsoids, elongated along 1 or 2 axes. Less massive halos tend to be more spherical. Massive halos are more flattened or elongated. The shapes correlate with the surrounding large-scale structure. The major axis of a halo tends to point toward nearby filaments or clusters. This alignment reflects the anisotropic nature of gravitational collapse. Matter falls into halos preferentially along filaments, not uniformly from all directions. Inside each halo, the simulations reveal substructure. Smaller halos that have merged into a larger host halo don't disappear entirely. They survive as subhalos, orbiting within the potential well of the host. As they orbit, tidal forces from the host strip away their outer layers, reducing their mass. Dynamical friction, a gravitational drag effect, causes them to lose orbital energy and spiral inward. Eventually, some subhalos are disrupted entirely. Their particles spread throughout the host halo. Others survive for billions of years. This substructure is critical for understanding galaxies. Each subhalo in a simulation could host a satellite galaxy. In the Milky Way, we observe dozens of satellite galaxies orbiting our galaxy, small dwarf galaxies like the Large Magellanic Cloud, the Small Magellanic Cloud, and many fainter ones. Simulations predict many more subhalos than we observe satellites. This is called the missing satellites problem. Either dark matter produces more subhalos than simulations predict, or many subhalos don't form stars and remain dark. Many subhalos are probably out there, invisible, ghosts within ghosts. The largest and most detailed simulations, like the Illustris project and its successors Illustris TNG, simulate not just dark matter, but also gas, stars, black holes, and all the complex astrophysical processes that turn dark matter halos into galaxies. These hydrodynamical simulations are computationally expensive, requiring months of runtime on supercomputers and producing petabytes of data, but they allow us to compare simulated galaxies directly with observations. The agreement between simulations and observations is remarkable. The simulations reproduce the observed distribution of galaxies, the clustering on large scales, the structure of the cosmic web. They reproduce galaxy properties like sizes, shapes, colors, rotation curves. When something doesn't match, it tells us something important. Maybe the dark matter model needs adjustment. Maybe the astrophysics of star formation and feedback is more complicated than we thought. Recently, machine learning has been applied to simulations, training neural networks to predict halo properties from initial conditions or to identify halos in simulation data more efficiently. These techniques are accelerating progress, allowing researchers to run larger simulations and analyze them more quickly. The picture that emerges from decades of simulation work is clear. Dark matter halos form through hierarchical merging. They have characteristic density profiles and shapes. They contain substructure, and they provide the gravitational scaffolding onto which ordinary matter falls, forming stars and galaxies. Without dark matter, galaxies as we know them couldn't exist. The universe would be a very different place, perhaps one where structure formed much later, where galaxies were smaller and more fragile, where life had less opportunity to arise. The cosmic web structure that emerges from simulations is breathtaking in its complexity and its simplicity. On the largest scales, matter is not distributed uniformly. Instead, it's organized into a network of filaments, sheets, and nodes, with vast, empty regions called voids in between. Galaxy clusters sit at the nodes where filaments intersect, places where matter has accumulated over billions of years. The filaments themselves are structures hundreds of millions of light-years long, but only tens of millions of light-years across, channels of enhanced density connecting the clusters. Some filaments contain chains of galaxy groups strung like beads along their length. The sheets are two-dimensional structures, walls of galaxies that separate the voids. The voids are the most striking feature. These are regions of space, sometimes 100 or 200 million light-years across, where very few galaxies exist. The density of matter in the voids is perhaps 10 or 20% of the average density of the universe. Matter has drained out of these regions, flowing along density gradients toward the denser filaments and clusters. Walking through the universe along a path that takes you through a typical void would be a lonely journey. You might travel 50 million light-years and encounter only a handful of dwarf galaxies, faint smudges in the darkness. This structure isn't imposed by anything external. It emerges naturally from gravity acting on the initial density fluctuations. Start with random fluctuations, let gravity amplify them, and you get filaments and voids. The pattern is robust. Different simulations, starting from different initial conditions, but with the same statistical properties, produce cosmic webs that look qualitatively similar. The details differ, the specific locations of clusters and filaments, but the overall character is the same. This tells us something profound. The large-scale structure of the universe is determined primarily by gravity and dark matter, not by the complex physics of galaxy formation. Dark matter creates the scaffolding. The filaments are made mostly of dark matter. The clusters are dominated by dark matter. Even the voids contain dark matter, just less of it. Ordinary matter, the baryonic matter that makes up stars and gas, follows the dark matter. Gas falls into the dark matter potential wells, accumulates in the centers of halos, cools in fragments to form stars. Galaxies form where dark matter halos are. The distribution of galaxies traces the distribution of dark matter, though not perfectly. Galaxies are biased tracers. They preferentially form in the densest regions, in the most massive halos. But the overall pattern, the web-like structure, is set by dark matter. Observations confirm this picture. Large Galaxy surveys map the three-dimensional distribution of galaxies across billions of light years. When you plot those galaxies in a three-dimensional map, you see the cosmic web, filaments stretching across hundreds of millions of light years, walls of galaxies, vast voids. The Sloan Great Wall, a structure 1.37 billion light-years long, is one of the largest known structures in the universe. A coherent filament containing hundreds of thousands of galaxies. The Boötes Void, 330 million light-years in diameter, contains only 60 known galaxies, where you might expect to find 2,000. These structures are real, and they match the predictions of dark matter simulations. For all that we've learned about dark matter over the past 50 years, profound mysteries remain. Perhaps the most puzzling is the diversity of ultra-diffuse galaxies. How can objects like Dragonfly 44 exist, seemingly dominated by dark matter with mass-to-light ratios 20 or 30 times higher than normal galaxies, while other UDGs like NGC 1052DF2 appear to contain almost no dark matter at all, with mass-to-light ratios consistent with their visible stars alone? How can galaxies of similar size, similar morphology, similar locations within galaxy clusters have such radically different dark matter content? What determines whether a galaxy forms with abundant dark matter or almost none? One possibility is that galaxy formation is more stochastic, more variable, more sensitive to initial conditions and environmental factors than we've appreciated. Small differences in the timing of formation, in the local density environment, in the presence or absence of nearby massive galaxies could lead to wildly different outcomes. A galaxy that forms early, in isolation, in a relatively massive dark matter halo might retain its dark matter and its gas, forming stars efficiently over billions of years and ending up as a normal spiral or elliptical galaxy. A galaxy that forms in the same mass halo, but in a different environment, near a massive cluster, might have a very different fate. As it falls toward the cluster, it would encounter the hot intracluster medium, a diffuse plasma of gas heated to tens of millions of degrees. This gas has low density but high pressure. When the galaxy plunges through it at speeds of hundreds or thousands of kilometers per second, the galaxy experiences ram pressure, like the pressure you feel when you stick your hand out of a moving car window. This pressure can strip gas out of the galaxy. Star formation requires gas. Without gas, star formation stops. The galaxy fades, becoming diffuse as its existing stars age and the brightest, most massive stars die. But the dark matter halo, which doesn't interact with the intracluster gas at all, remains intact. You end up with a dark matter-dominated ultra-diffuse galaxy. Alternatively, some UDGs might form through tidal interactions, gravitational encounters between galaxies. When two galaxies pass close to each other, tidal forces, the differential gravitational pull across the body of each galaxy, can pull out streams of stars and gas. These tidal tails can extend for hundreds of thousands of light years. Sometimes, the material in a tidal tail can collapse under its own gravity to form a tidal dwarf galaxy. These tidal dwarfs are born from material that was already in the outer parts of their parent galaxies, regions where dark matter density is low. They might form without significant dark matter halos because the material they're made from simply didn't contain much dark matter to begin with. This could explain why some UDGs lack dark matter. But these explanations are not fully satisfying. The diversity seems too great, the range of properties too wide. For every rule we propose, there's an exception. We need more observations, more detailed studies of individual galaxies, more sophisticated simulations that can capture the full complexity of galaxy formation, including gas dynamics, star formation, supernova feedback, and environmental effects. The diversity of UDGs is telling us something important about how galaxies form and evolve. We just don't fully understand the message yet. Another deep mystery concerns modified gravity theories. While the evidence for dark matter is overwhelming, especially from gravitational lensing studies like the Bullet Cluster and from the cosmic microwave background, some physicists continue to explore alternatives. Modified Newtonian dynamics, or MOND, proposes that Newton's laws break down at very low accelerations, the kind found in the outer parts of galaxies. Instead of force being proportional to acceleration, as Newton stated, the relationship becomes nonlinear when accelerations fall below a critical value of about 1/10,000,000th of a meter per second squared. By modifying the gravitational force law in this way, MOND can reproduce flat rotation curves without invoking dark matter. MOND works surprisingly well on galactic scales. It fits rotation curves of spiral galaxies with impressive accuracy, often better than dark matter models that have multiple free parameters. This success is intriguing and demands explanation. Why would a purely phenomenological modification of gravity happen to match observations so well? Some physicists argue this suggests we're missing something in our understanding of gravity or inertia, that MOND is pointing toward a deeper truth. Others argue it's coincidence, that dark matter happens to be distributed in galaxies in a way that mimics a modification of gravity on small scales. But MOND struggles on larger scales. It has difficulty explaining galaxy clusters without invoking some additional dark component. It cannot explain the Bullet Cluster, where the separation between mass and baryonic matter is clear and dramatic. It has trouble with the cosmic microwave background, which shows acoustic peaks that require dark matter to form at the right redshift. Most physicists view MOND as an interesting phenomenological description on galactic scales, but not a fundamental theory that can replace dark matter. Still, the fact that MOND works as well as it does is intriguing. Perhaps it's telling us something about the relationship between dark matter and ordinary matter that we don't yet understand. Perhaps dark matter interacts with baryonic matter in ways beyond just gravity. Self-interacting dark matter models, where dark matter particles scatter off each other through forces other than gravity, are being explored as one possibility. Other exotic possibilities remain on the table. What if dark matter particles interact not just through gravity, but through a weak self-interaction? Self-interacting dark matter, or SIDM, proposes that dark matter particles occasionally scatter off each other. This would affect the structure of dark matter halos, potentially solving some discrepancies between simulations and observations, like the core cusp problem. Simulations predict halos should have cuspy centers, where density rises steeply toward the core. Some observed galaxies seem to have flatter cores. Self-interactions could smooth out the cusps. Primordial black holes, formed in the very early universe from density fluctuations, have been proposed as a dark matter candidate. If these black holes have masses in certain ranges, they could make up a significant fraction of dark matter without contradicting observations. Recent gravitational wave detections of merging black holes have revived interest in this idea. Could some of those black holes be primordial? Could they be dark matter? It's possible, but current constraints from gravitational lensing and other observations suggest primordial black holes can't account for all dark matter. They might contribute, but they can't be the whole story. Sterile neutrinos, a hypothetical type of neutrino that doesn't interact via the weak force, have also been proposed. Unlike ordinary neutrinos, which are too light and move too fast to be dark matter, sterile neutrinos could be heavier and slower, qualifying as cold dark matter. Some experiments have hinted at anomalies that could be explained by sterile neutrinos, but the evidence is tentative. The search continues. Perhaps the most humbling possibility is that dark matter is something entirely unexpected, something we haven't imagined. The history of physics is full of surprises. Atoms were once considered indivisible. The nucleus was discovered by accident. Quarks were a theoretical construct before experiments confirmed them. Neutrinos were proposed to save energy conservation and turned out to be real. The universe has a habit of being stranger than our theories. Whatever dark matter turns out to be, the search for it is pushing physics into new territory. New detection techniques, new experiments, new theoretical frameworks. This is how science progresses, by confronting the unknown and refusing to accept ignorance as permanent. Every null result, every experiment that finds nothing, still teaches us something. It rules out possibilities. It narrows the search space. Eventually, we will find the answer, or we will be forced to completely rethink our understanding of gravity and cosmology. Either outcome would be revolutionary. We live in a universe where 85% of the matter is invisible. Everything we see with our telescopes, every star cataloged, every planet discovered, every nebula photographed, every galaxy mapped, represents only a small fraction of what's out there. The rest is dark. The rest is ghost. We are surrounded by it, immersed in it. Right now, as you lie here reading these words, dark matter particles are streaming through your body, billions upon billions of them, passing through you and through the Earth as if you weren't there, traveling on their ancient orbits through the Milky Way's dark matter halo. They pass through without leaving a trace, without interacting except through the faint tug of gravity. This should be humbling. We pride ourselves on our understanding of the universe. We've measured the age of the cosmos to within 1%. We've traced cosmic history back to a fraction of a second after the Big Bang. We've detected gravitational waves from merging black holes billions of light years away. We've imaged the shadow of the event horizon around the supermassive black hole at the center of Galaxy M87. These are extraordinary achievements, testaments to human ingenuity and persistence. And yet the most abundant form of matter in the universe remains unknown to us. We don't know what it is. We don't know what it's made of. We can see its effects, map its distribution, measure its mass, but we cannot capture it in our detectors or produce it in our accelerators. Not yet. Vera Rubin spent her career studying these ghosts. She passed away on the 25th of December 2016 at the age of 88, having transformed our understanding of the cosmos. She never received a Nobel Prize, an omission that many in the scientific community view as a glaring oversight. Some attribute it to the Nobel Committee's historical neglect of astronomers, as the Physics Prize tends to favor theoretical breakthroughs or experimental discoveries in controlled laboratory settings rather than observational work. Others suspect gender bias played a role, noting the long history of women being overlooked for scientific achievements. Rubin herself was ambivalent about prizes and recognition. When asked about the Nobel, she sometimes expressed uncertainty about whether she wanted it, saying it would change her life, not always in a good way. What mattered to her was the science, the discovery, the understanding. She was repeatedly told throughout her career that women didn't belong in astronomy. Princeton's rejection letter was blunt. Colleagues dismissed her early work. She was excluded from conferences, denied access to telescopes, questioned about her competence. She proved them wrong through the clarity of her data and the strength of her persistence. She opened doors not just to the dark universe, but for women in science, mentoring generations of astronomers, advocating for equality, insisting that scientific meetings include women speakers, threatening to boycott conferences that didn't. Her scientific legacy is matched by her human legacy. Her legacy lives on. In late 2019, the Large Synoptic Survey Telescope in Chile was officially renamed the Vera Rubin Observatory, with the formal announcement made in January 2020 at the American Astronomical Society meeting. It's the first major U.S. When it becomes fully operational, it will survey the entire southern sky every few nights, capturing billions of galaxies and helping astronomers probe the distribution of dark matter across cosmic time. It's a fitting tribute. Rubin opened the door to the dark universe. Now an observatory bearing her name will explore that universe in unprecedented detail. The search for dark matter continues in laboratories around the world, in experimental facilities carved deep into mountains and hillsides to escape cosmic ray backgrounds. Deep underground in South Dakota at the Sanford facility, in Italy beneath Gran Sasso, in universities where theoretical physicists develop new models, propose new candidates, calculate new predictions for how these particles might behave. In simulation centers where supercomputers run the universe forward in time, testing whether our theories can reproduce what we observe. In observatories scattered across mountaintops and deserts that map gravitational lensing with ever greater precision, measuring the distribution of the invisible. Each experiment, each observation, each simulation adds a piece to the puzzle. We don't yet know whether dark matter is made of WIMPs or axions, or something else entirely, some particle or phenomenon we haven't even conceived of yet. We don't fully understand why some galaxies are almost entirely dark, while others have almost no dark matter, or what this dramatic variation tells us about the processes of galaxy formation and evolution. We don't know if dark matter self-interacts through some unknown force, or if it's completely collisionless, feeling only gravity. These are open questions, active areas of research, frontiers where our knowledge ends and mystery begins. But that's what makes this science exciting, what draws researchers to spend careers in pursuit of the invisible. We're standing at the edge of a great mystery, peering into the darkness, waiting for the next clue, the next observation that might illuminate what has been hidden. Ghost galaxies like Dragonfly 44 serve as laboratories. They're places where dark matter dominates, where its properties should be easier to study because there's so little ordinary matter to confuse the picture. Ultra-diffuse galaxies challenge our understanding of galaxy formation. They force us to confront the diversity of the universe, the fact that nature doesn't always follow simple rules. The bullet cluster and other colliding clusters show us dark matter in action, separating from ordinary matter, revealing itself through gravitational lensing. These cosmic collisions are natural experiments, events we could never create in a laboratory, but that the universe performs for us on the grandest scales. The simulations tie everything together, connecting theory with observation, allowing us to test whether our models of dark matter can reproduce what we see. When the simulations match reality, we gain confidence. When they don't, we learn something new. 50 years ago, Vera Rubin stood in an observatory, puzzled by flat rotation curves. Today, we have a wealth of evidence for dark matter, from multiple independent sources, all pointing to the same conclusion. Dark matter is real. It's out there. And slowly, carefully, we're learning its secrets. The universe is patient. It's been keeping its secrets for 13.8 billion years. A few more years or decades, while we figure out the nature of dark matter won't matter on cosmic scales. But for us, for humanity, every discovery is precious. We are creatures of light, made of atoms that emit and absorb photons, living on a planet bathed in sunlight, seeing the world through electromagnetic radiation, it's natural that we think of the universe as the things we can see. But the universe is not just what we see. Most of it is hidden. Most of it is dark. We live in a cosmos dominated by ghosts, and perhaps that's appropriate. We are a minority, a peculiar form of matter that happens to interact with light. The ghosts around us, the dark matter streaming through this room, through our bodies, right now, are just as real as we are. Perhaps more so. There's more of them than there is of us. So as you lie here in the darkness, drifting toward sleep, consider the invisible universe around you. Dark matter particles passing through the earth, through the walls, through you. Galaxies made almost entirely of darkness, scattered across billions of light years. The cosmic web of dark matter filaments, connecting clusters, shaping the architecture of the universe. All of it invisible, all of it real, all of it waiting to be understood. The ghosts are there. If you enjoyed this exploration of the dark universe, consider subscribing to the channel and leaving a like. It helps more people discover these long-form deep dives into cosmic mysteries. There's so much more to explore, so many more stories waiting in the darkness. Until next time, sleep well and dream of galaxies.